Hello everyone, we're Team GMAT 770. We are focusing on teaching and training GMAT test takers all over the world, especially in North America and in Asia. Our goal is to help GMAT test takers to pass GMAT tests before they apply for graduate schools all over the world. The test score of each of our team members is about 750, and the co-founders of our team got GMAT test score 770, so that's the reasons why we call this name. I'm the math teacher, Corinne, of our team, and I hope that from these lessons about math, you will easily pass quantitative parts in GMAT test. So are you ready? Let's get started.
Hello everyone, welcome to our lecture, Combination, Permutation, and Probability Part 2. If you hasn't walked through our last lecture, Combination, Permutation, and Probability Part 1, I highly recommend that before you move on to this lecture, go back to have a quick review of our last lecture, Part 1, since the last lecture include some definitions and basic rules of this topic. In today's lecture, we will walk through some special kinds of questions in combination, permutation, and probability. Okay, so the first kind of questions, first method you will use in combination permutation questions is binding method or bundling method. So what does that mean and how it can work? Let's use an example to explain it. How many different sequences can be formed using four letters A, B, C, and D, and A and B must be placed adjacent to each other? So first, let's have a better understanding of this question. A and B must be placed adjacent to each other, which means that letters C and D cannot be placed between A and B. So first, we can combine letters C, A, and B together as a group. And then letter C and letter D. Another two groups. So right now we have three different groups. So first, we can place the three different groups in order. So we use P33 to represent the sequence of the three groups. And right now that we place the three groups in order, and within the first group, A and B also had a sequence. So we must also multiply by the sequence between A and B, which is actually P22. To get the answer to this question, which is 12. So in these questions, we have two procedures. The first procedure is the sequence between the three different groups. And second procedure is the sequence within the group, the sequence of the two elements in the first group. There are two procedures. So when you see that question is asking that some elements must be placed together or some elements must be placed adjacent to each other, we can first combine those elements together as a group and place the groups in order first. And second, don't forget to multiply this sequence within the groups. The second method you will use is plug-in method. Also, we use an example to explain it. A, B, C, D, E, and F are going to watch movies tonight, and their seats are consecutive and in the same row. How many different ways are there if A, B, and C cannot sit next to each other? So first, let's explain that what does it mean that A, B, and C cannot sit next to each other? It means that D, E, and F, at least one of them must be placed between A and B, B and C, and also A and C. So in these questions, there are no more requirements for the sequence of D, E, and F. So we placed D, E, and F in order first. We use P33 to represent the sequence of D, E, F. After we place D, E, and F in order, we will have four different intervals, 1, 2, 3, and 4. And A, B, C must be placed into different intervals so that A, B, and C can sit separately. So we choose three different intervals from the four intervals to place A, B, and C, and also the sequence does matter. So we use P43, not C43 to represent that. So P43 represent that we choose three different intervals to place A, B, and C. So these are two different procedures, so we multiply them together to get the answer to these questions, which is equal to 144. So if you see a question as asking for that some elements cannot be placed together or some elements must be placed separately, you can use plug-in method. So first procedure is you can place those elements has no more requirements for their sequence. First, to form different intervals and choose different intervals. To place those elements must be placed separately. Okay, so the third kind of problem we'll face in combination and permutation is round table problems. It is special kinds of problems because right now, all the questions we solve are about a line, not about circle. So we must figure out the difference between a line and circle, so we use a question to explain it. How many different ways are there for 6 people sitting around the table? Well, if I change the question into how many different ways are there for 6 people sitting along the line, you can easily figure out the answer is P66, which is equal to 720 to represent the sequence for 6 people sitting along the line. But how many different sequences can be formed for 6 people sitting around the table? So let's see the difference between a line and a circle. Let's draw a line first. As we can see that a line has a starting point and ending point, but a circle, it doesn't have a starting point and ending point, so that's the difference between a line and a circle. So how does this difference change the answer to this question? Okay, so there is one sequence for 6 people sitting along the line is 1, 2, 3, 4, 5, 6, 1 on the left side and 6 on the right side. And then you move rightwards each of them one place and move the 6 from the right side to the left side. So it's gonna change into 6, 1, 2, 3, 4, and 5. And then you follow the same rules and move them again. It will change into 5, 6, 1, 2, 3, 4. And then 4, 5, 6, 1, 2, 3. And then 3, 3, 4, 5, 6, 1, 2. And then 2, 3, 4, 5, 6, and 1. And then the next time it's gonna change back into 1, 2, 3, 4, and 5, and 6. So the 6 different sequences, there are different sequences for people sitting along the line, but actually if you connect the starting point and ending point of each line end to end and to form a circle, you can see that they are actually the same for a circle. So every 6 different sequences in a line can form one sequence in a circle. So how many different sequences in a line is P66? So how many different sequences can be formed for 6 people sitting around the table? You can just divide it by 6 to get the answer to this question, which is 120. Okay, so let's move on to questions of probability. The first question is quite basic. In a box of 12 pens, a total of 3 are defective. If a customer buys 2 pens selected at random from the box, what is the probability that neither pen will be defective? Well, as we learned before, how we get the probability of this question is just divided the outcomes that satisfy with this question by all the outcomes in this question, which is actually a ratio. So what is all outcomes in this question is actually you can just select 2 pens randomly from the 12 pens, right? So which is say 12, 2 to represent this. This is actually all the outcomes. And what is the outcomes that satisfy with this question is those 2 pens selected will be not defective. So you have 12 pens. 3 of them are defective, which means that 9 of them are not defective. Neither pens will be defective, which means that the 2 pens chosen will be from this 9 pens, right? So C92 represents that the 2 pins selected will not be defective. So this is actually the outcomes that satisfy this question. So you can easily get the answer as 611. So here's another examples of probability. A, B, and C each try independently to solve a problem. If their individual probabilities for success are 1/4, 1/2, and 5/8 respectively, what is the probability that a problem will be solved? So the key word of these problems is individually. So which means that whether A solves this problem will not affect B and C. So what does it mean the problems will be solved? If one of them or two of them or even all of them solve this problem, the problem will be solved. So if you think about this question directly, you will find out there are many different kinds of situations can satisfy with this questions. But if you think about this question conversely, what does that mean the problem will not be solved? So actually, if none of A, B, or C solve these problems, the problem will not be solved. And that is actually the only one situations for the problem not be solved. So in this way, we can use 1 to minus the probability for the problem not be solved to get the probability for the problems will be solved. As A, B, and C each independently solving these problems, so the probability for none of them solving these problems was actually equals to the probability for A not solving this problem multiplied by the probability for B not solving these problems and multiplied by the probability for C not solving these problems. So it should equals to 3/4 multiplied by 1/2 and multiplied by 3/8. And this is actually for the probability the problem will not be solved. So it is equal to 9 out of 64. And you use 1 to minus the probability for problem not be solved to get the probabilities for the problems to be solved. So it should equals to 55 out of 64. This is the end of our lecture, Combination, Permutation, and Probability. In Part 1 lecture, we have some basic understandings of the definitions and rules of the three concepts. And in Part 2 lectures, we move on to some more difficult questions and learned about some methods to solve these questions. Hope these 2 lectures will help you to figure out combination and permutation related questions. While our next lectures will move on to a new chapter. Hope to see you again. Bye.